So basically, this is what I'm going to discuss in the demonstration today. Suppose let's say we are having certain dam like this, and we need to find the factor of safety for this particular dam. So what I will do is I will model the dam without the seepage forces because of the initial water level or any transient seepage, and I will run the analysis to find the factor of safety. So I will without any seepage, and then again I will run the analysis with this steady state seepage as well as this transient seepage, which is going to reduce because of the transient nature, the rapid drawdown or something like that, and how the factor of safety is going to vary on your left side and right side of your dam. So we will see them and we can get to know how the phreatic surface or how the seepage forces are going to have a complete different behavior of your slope. So now what we need to do is we need to model this particular dam. We need to apply certain materials to it, and then we will run the analysis for both and considering and without considering the seepage, and we can see the results. So this complete modeling will be done in SoilWorks, and so this is a very famous picture, and this is you can see the buildings getting tilted and getting almost completely destroyed because of the liquefaction on this complete area. So what we do is I'm having certain building with me. I'll be modeling that building in in MIDAS Gen. That's our structure software, and I will be exporting that structure software model to GTSNX, and I will model the soil layers and even the liquefiable layer as well, and we can see the results how that is going to affect the building. So that's what about the building. Now we will go for the demonstration of your SoilWorks now. So basically we will be going for SoilWorks model now. Just give me a minute. I will just open the required models, and then I will just able to replicate the same in the SoilWorks software, and we will run the seepage analysis followed by your slope stability analysis. So whenever we open the SoilWorks software, it will ask you for these different modules. So let's say we are running a seepage module in the very first case. We are opening the seepage module, and we will run the seepage analysis followed by the slope stability analysis. So I will just generate the model, and I'm already having certain model with results with me. So I will show you that results. So just go to seepage module. So now the seepage module is going to open. Yeah. So this is how the interface looks like. In the very first case, we got a geometry and followed by model, followed by boundary and analysis, and we got tools and windows. So this is about the ribbon menu, and we got certain tools regarding to this particular commands in this particular ribbon menu. So this is your work tree. So what type of works you do from starting to ending will be listed over here, and you can able to edit it in the later part of the time as well. So this is what I'm going to model. So this is your complete dam, let's say a 2D model, and I will be modeling them in a seepage, first seepage analysis basically, and then I will run let's say a coupled analysis by completely transferring this model to slope model, and I will be directly taking the results of the seepage results, and then I will apply them in this slope model, and then we can see the results how it is going to change. So in the very first case, we are going to run a seepage analysis, taking the results of seepage and applying them in the slope model. As simple as that. Yeah. So what we can do is, let's say I can able to model them using these particular features of using the commands of your line or rectangle, or else you can directly model them by using certain grids. And this is one way of approach, and apart from this you can able to model them by using AutoCAD features. So what I can do is, I'm just giving you a rough idea how to model by using grid in this particular example, but apart from this I'm directly importing the AutoCAD file from already existing AutoCAD file now. So this is how we can model it, or else we can use the rectangle and followed by smart surfaces. So I will be giving you the rest of the features now. So just go to this first tab, File tab, and you go have Import Model, and go to CAD File. So what we do is we will import the AutoCAD file. Yeah, so here we got the AutoCAD file with us. So this is your complete AutoCAD file. It has been completely modeled in AutoCAD, and what we have done is we have imported them into SoilWorks. So this is your dam casing, this is your existing leaf, let's say this is my embankment, this is my filter or riprap, and we got three different layers. So what we do is we go for smart surface now. So whenever you click the smart surface, what you can find is you can able to see the complete model getting the surfaces. So with one click, the complete model is finding the surface. So what you do is you need to assign properties to it. So for that, go to model, and here in the ground properties, we need to provide horizontal permeability, vertical permeability, volumetric water content, or unsaturated properties if you're having any. So only these are required for this particular analysis to be done. Because we are running a seepage analysis and it's not a stress analysis, so we are not interested in the strength parameters like cohesion or friction angle, but we are interested in the flow paths or equipotential lines because of the seepage results. So here we are having these particular properties for different materials. I will just apply one material, and then I will import the rest of the materials, because we got riprap, we got your existing leaf, we got embankment, we got three different layers. So the very first layer, so let's say the very first one is embankment. Give the name as embankment. Let's say the permeability in terms of meter per seconds, we can consider like 4.17 E minus 7, so nothing but 4.15 into 10 power minus 7 meter per second. Let's say this is same as well in my horizontal and vertical direction. Basically it will be different, but in this complete model we are considering the horizontal vertical permeability as the same, and we will run the analysis so that we can able to find the results for the inputs which I have given, and then just press add. So your embankment has been added. So what I do is I will directly import the already existing file. I will import the database for applying the inputs from already existing file. So go to import, import data phase from the another file. Yeah, so now we will directly go into ground data. We can see all the data has been imported. So this is for your embankment layer, existing leaf, alluvial layer. So this is your alluvial layer. The next one is your weathered soil, and this is weathered rock. And this is your riprap, nothing but our filter. So what are the properties that has been assigned for each and every of them will be seen now. So this is what I have defined earlier, and this is what already I have imported from the existing model. So what I do is I will just delete the first one. This is the embankment layer. Here we can see the permeability coefficients in both x and y directions. And then we got some unsaturated property for this particular embankment. So this is my embankment. Just go and see what type of property that has been assigned. So this is your unsaturated property of your particular embankment soil. With respect to load, what is the K ratio, how it is varying, and with respect to pore pressure, what is the water content that is being varied. So that's what we need to define in terms of like unsaturated soils. So basically even your unsaturated soils can able to be applied in the software and you can run the analysis. Similarly for existing leaf, so this is your already existing leaf, and we got certain permeability coefficients of 10 power minus 6 meter per second and unsaturated property of some kind like this. What could be the pore pressure ratio with pressure load versus your K ratio, and pressure load versus your water content and alluvial layer. So this is my all inputs. So I'm saying the software how this can be able to behave based on the inputs I'm giving. So this is the alluvial layer again, and alluvial layer is also having certain functions of your unsaturated property. With respect to load, how my K ratio is going to define, vary, and with respect to pore pressure, what could be the water content variation. So this is what I'm going to define for all the cases. And then weathered soil, similarly weathered rock, and now we'll see for riprap. So riprap is like a filter for me, and what we need to do is, why we are providing filter is we want all the seepage which is coming from the upstream to go through the filter or riprap. So we need to have a gravel, something like gravel. So for a gravel, the permeability will be very high, and that's why I'm providing very high permeability. So whatever water which is like a seepage which is passing through the soil layers will go through this riprap because it is having high permeability. So the soil, this can able to attract water, and the water which is coming from here can able to take. And this can able to add the stability to the structure, because for gravel the strength parameters will be high, and but permeability is very high as well, so that the water which can be coming through the filter can be directly taken and can be drained as well. So that's your ground parameters. Now what I will be doing is I'll be assigning these parameters to the I will be assigning these parameters of soil already defined soil layers to the existing structure. So let's say this is my existing leaf, and I will just drag and drop so that this particular layer will be having the existing leaves material. So directly you can check it. So here you can see it is having existing leaf property. And then similarly we will assign the embankment, but we'll just select only this surface. This is embankment layer, and we will select the riprap, and we will just add them. Select the alluvial layer, drag and drop, select your weathered rock, again drag and weathered soil layer, and drag and drop your weathered soil property, and select your weathered rock and drag and drop your weathered rock. So as simple as that. So what we have done is we have generated the geometry, and we have generated the smart surface, and we have drag and drop each and every layer. Like let's say this is riprap. So what for one surface, riprap has been defined. So what is the surface? Yeah, this is the surface. Or else you can able to find them in the object information as well. So I've selected this surface. This has been provided with the ground material property of embankment layer. This layer again is having alluvial layer, and the very last one is having weathered rock. Yeah. So what I want to define and I have defined it correctly. So the very in the bottom one is weathered rock, second last layer is weathered soil, the top layer is alluvial, and this is existing leaf, embankment layer, and riprap. So this is about a simple modeling, And now what we do is we will directly run the analysis for seepage. So for seepage analysis, we need to apply certain boundary conditions. So we will apply those boundary conditions now. So the boundary conditions like head and total head and transient head, if you're having certain one, so we need to apply them now. So what we need to do is we need to mesh them before applying any kind of nodal head or let's say transient head. So we are having certain smart mesh with us. Just go to very fine mesh and just press OK. The entire model will be meshed by itself. If you want to generate higher order elements, you can able to generate higher order elements so that it can able to find the mid-side nodes as well. And yeah, so let's say I want to apply certain head now. 1 minute. Yeah. So let's say I want to apply certain head onto the existing structure. So this is my upstream. So I want to apply certain head, let's say a head of 18 meters, so that would be my total head. And on the bottom side, I would be applying a zero head, or let's say if 50 certain water level of 2 meters, so I will be applying head of 2 meters. That is my total head. So basically what I'm doing is I'm telling the software that it is having certain head in upstream and downstream. So I'll be applying them now. Yeah. So let's say here go to boundaries and go to nodal head. So let's say this is an upstream head. And instead of nodals, I will select the curve. So this is my upstream. And I'll say it is having 18 head. That's nothing but total head, or you can even provide pressure head. And if you're having any function, what you can do is you can provide the function. So that's as simple as that. Nothing but your function of transient seepage, how it is varying with respect to time. So that's what it represents. Here you can see, let's say this is varying with respect to like this. I will apply them now. But as of now, I'm applying a steady state head. So let's say I will write steady state. Let's press apply. So here on the upstream side, I'm having a steady head of 18 meter. And now this, let's say I'm applying a head on the downstream. Let's say I'm not having any head on the downstream. This is like completely dry and it is not having any water level. If you're having any water level, you can directly select the layers and you can apply them. That's not that's how you have done in the upstream side. Similarly, you just select your surfaces. If you're having, let's say, 2 meters on the downstream, I will apply head of 2 meters, just like that. But let's say I'm not applying any head and it is having a head of 0. So what I do is I will provide a review boundary in here. So this is your review boundary, which is having a 0 head. So I will just say that the software, this is my review boundary, which means it is having 0 head. Apply. So it's having 0 head. Now I will ask the software to run for a transient seepage as well, so that I need to apply certain function to it. So just go to nodal head to again and provide transient seepage. Yeah. So let's say we will apply value of 1 in here, and why I'm applying value of 1 I will be telling you. Again, this transient seepage is on a like a upstream side. So I have already defined one function. So go for water level function, and what this water level function, we will just have a look in here. In this water level function, you're having with respect to time, this is in terms of seconds, and this is a value. So your time in the very starting, this is 0, and your head is of 15. That means it is in the very first time, it is having a head of 15 meters. And with respect to time, it is increasing to 18.42, and again it has been increased, and it is staying stagnant over here, and then it has been suddenly reduced. If you're having certain rapid drawdown, you can able to simulate them in the form of this particular transient function, and in the very last stage, you're having the value of 15 again. This is what your transient seepage means, and we have inputted in the form of transient seepage with respect to time versus your value. And now let's say this is your total head value. So since you have considered the total head, and this will be multiplied with 1. So this one is a factor now. So this one will be multiplied with this particular value. So if you provide a head of 10 again, so the value will over here will be like 15 into 10, so it will be 150. So this is your function. So this is not normalized 1, so I'm keeping the value of 1 over here. So just close it. So this is my total head, and this is of 1. Just say OK. So basically now you have defined your functions, seepage functions, and you have applied certain unsaturated functions in here. This is what you have done till now. You have developed the geometry, so this is your geometries, and then you have developed the mesh. These are your mesh sets, and then you have developed the properties and you have assigned them. You have developed the function, you have assigned them, and you have assigned them in the form of boundary conditions now. Now we just go into analysis. So go to analysis case, go to add, and here let's say steady state. So use all mesh sets, and in the boundary condition use upstream head state. So we are using the upstream head state and a review boundary. This is for steady state. So this is for steady state, and this is all your analysis control, let's say, and just press apply now. And now go for transient seepage analysis. So whatever steady state which has been generated, I'm just dragging it to the all mesh sets, and I'm activating my transient seepage. So this is my transient seepage. Let's give the name as transient seepage, and just press analysis control. You need to provide certain time steps to it. So here we are having certain time steps. Let's say you're having a time steps of with respect to the bound, like let's say, yeah, I will show you once again the boundary function which has been defined by me. So go to nodal head, and here you want a result at the time of 0, 1 to 9, 600, 17 to 800 seconds, and 259, 200 seconds. So what I will do is I will define the time steps at these particular values, so that at these particular time steps I will be having certain results. So what I will do is I will just go to analysis case again, boundary analysis. Here go to add, and go to transient seepage. Use all methods and use review boundary and transient seepage. Provide the name as transient seepage. Go to analysis control, and here go to time steps once again. You can either provide your complete time steps. Let's say you're having total time of 259, 200 seconds. 259, 200 seconds, and let's say you want to create the steps. So this is only 259, 100. So you can able to auto generate it, or else you can able to generate it with respect to time. So what I will do is I will just delete this one, and I will just generate a new case where I want to have a result at a 0 second, create step. I want to have a result at 129,600 seconds, create step again, and I want to result at 172,800 seconds. Oh, sorry. That's my bad. I will just create once again. 0 second, just save results. And in the second step, you're having 129,600. Create. Or else you can able to provide for auto generation of 259,200, and you want to change it into 4 steps, just create steps. So all these steps has been created. Or else if you want a result and accurate results at each and every different interval, so you can change the number of steps as well. So these are the steps which has been provided by me. Just press OK, close. Now what we do is we will run the analysis. Go to analysis and just run. So I need to save this somewhere. Let's say I will provide a new folder. And I give the name as Seepage. It's performing and it takes just less than. And in the meantime, I will show you the results in already generated model. So yeah, the analysis has already been completed in here. So now we'll see the results. Just close it. And this is your steady state results. So you'll be having your all the results like your steady state ground seepage analysis as well as nodal seepage head. Let's say what could be the saturation. Yeah, this is how the saturation condition will be. What could be the saturation state? So you can see the results. What is the saturation degree of saturation basically. You can find the results at any point of your interest, and so this is one case. Now let's say I want to see the total head. So this total head will represent your equipotential lines. So what I do is I will just go for band. So this is different equipotential lines. So here you're having first steady state seepage. Now when we see the results for the transient seepage, we can see how equipotential lines are being varied with respect to the, like a change in the water level. So let's say these are my different equipotential lines, and you can find the value by using the legend, or else you can probe the result here. Just at this particular point, what could be the value, because this is your 18 meter head, and in the bottom you got 17.9. And what could be the result in here, 17.6, and as you go further your value is changing because here the water is getting drained, and here we got 14.4 head now. So this is how the total head is being varied. A maximum in the upstream, and since the seepage is going on, and you can find certain head over here now. And now what could be the pore pressure head? This is how the pore pressure head is, and we'll see the ferritic line now. Yeah, here you can see the ferritic line. This is my ferritic line. Water surface line will be, because since there is a riprap, your all seepage which is coming through is like going into the riprap. So that's why the water level is also getting suddenly decreased over here. So that's the function of riprap, because it is having huge permeability. Now we will see certain flow paths. And we can even find the volumetric water content, how much amount of water, and then the permeability coefficients. So the resultant permeability coefficients which I'm talking, and you can see the flow quantity as well. So these are all your input values. What I will do is I will just hide the boundary conditions. Yeah. So this is your results. In the flow quantities in the upstream side, you can able to see the results like this is how much of water that is getting inputted, and this is how much of water that is coming outside. So we'll change it into mm, so we can find certain value. So the input is high and output is very low, 32 mm cube, and here it is like a 1.4 into 10 power minus 5 mm cube. So that's one result, and now we'll see the results for the transient seepage. So I'll just close the steady state and we'll see the transient seepage at 4 different steps because I have considered the steps of 4 different to find the analysis results. So let's say at 64,800 steps, sorry, 800 time of seconds. What could be the phreatic line? So this is my phreatic line, and in the second time of 129,600, this is my phreatic line. You can see a simple change in the phreatic line, and I can see a simple change again, and you can see simple change again. So in the very last stage where you're having rapid drawdown. So this is how the phreatic lines are being changed, and now we'll see how the total head are being varied. So this is in the very starting case, and then in between we are having total head like this, and then total head, and then this is the last head. So when there is a drawdown, there is like a huge differences in your equipotential lines, and this is how the transient seepage can able to affect the seepage behavior of your complete slope. Now what we do is we will export this particular model to slope module. Directly go into here, just press S. Your model will be exported to a slope module. So here we are finding a slope module now. So nothing has been done. Nothing has been edited. What I have done just is I just completed the seepage analysis. I had completely exported the model to the slope module. So in order to export the module, you need to click in the very top where you're having a slope module. 1 minute. I just exported this into ground module, but similarly you can export the same into seepage like slope module. Since we are interested in running a slope analysis, I will export that into a slope module now. So till then I will just see the questions which we are having now. Sorry for the interruption. 1 minute. So this is our seepage module model, and what we do is here in the very top, this is your slope symbol. So just click over the slope symbol. So complete seepage module will be exported to your slope module. Yeah, so this is your slope module now. Yeah, so what you have done is now whenever you go for slope module, what it does is whatever model which you have generated in the seepage module will be completely exported, and even the material models will be exported. The only thing is we need to now introduce the strength parameters in here. So go to limit equilibrium method, and now go to structure, like let's say ground material, and here all the embankment layers, everything has been generated. So let's say as I said, in slope module we can able to run the analysis for finite element method as well as limit equilibrium method. So what I will do is I will just run the seepage analysis in combination with your limit equilibrium method. So how it can able to find the results, we will just go through it. So what we do is we will change the strength parameters for your particular cases. So let's say for riprap, I'm going to change the strength parameters because all the parameters which have been assigned in here are like a default values, because I have only assigned the permeability coefficients in the seepage results. So what I need to do is I need to assign the strength parameters now. Let's say my unit weight is of 22 and saturated unit weight of 23 and cohesion of 50 and internal angle of friction of 38. Just modify it. Similarly, go to weathered rock, and in the weathered rock, let's say my model type is for limit equilibrium method, so that unit weight is 21, saturated unit weight of 22, cohesion of 30 and a friction angle of 36. And now go to weathered soil, change the model type to LEM again, and let's say unit weight of 21, sorry, a weathered soil, right? Let's say the unit weight of your weathered soil is 20 only. Saturated unit weight of 21 and normal unit weight of 20. And let's say angle of internal friction of 35 degrees and a cohesion of 10 kilonewton per meter square. And now in the alluvial layer, change it into Mokulum again, LEM. Unit weight is 19, saturated unit weight of 20, and cohesion of 15, angle of internal friction of 32. Just modify them. And existing leaf. So for the existing leaf, we got certain model type, and that model type is of LEM again. Unit weight is 18, saturated unit weight of 19, cohesion of 5, and angle of internal friction of 25. Go to embankment, again change into LEM, unit weight 19, saturated unit weight of 20, cohesion of 5, angle of internal friction of 28. So this is what the modified strength parameters is, and those has been assigned to the different layers. So what we need to do is we need to provide certain arc failure surfaces, because we are interested in finite like limit equilibrium method. So what we need to do is we need to see the slope capacity of this particular means factor of safety of this particular left side slope and right side slope with the only self fit, and then we will add the seepage results, and now we will see what is the factor of safety with seepage for both steady state and transient. So go to arc failure surface, just draw a grid like this. So this will be acting like your grid for generation of your failure surfaces. And let's say a number of arc that's passing through each and every center is, let's say 10, means number of arcs which will be drawn with respect to the centers of each points in the grid is 10, let's say. Just say this is your left grid, apply. Similarly, you can find it on the right side as well, 0.5. and let's say 10 again, and press OK. Sorry, let's say we can find right grid. Just change the name as right grid now. Draw the grid again. So these are two different grids. What happens is from each point you can have a 10 different. So these are your different failure surfaces. So at each and every failure surface, you'll be having a different slices will be formed, and then the factor of safety will be calculated, and minimum of all will be considered as your factor of safety. Similarly to your right side as well. So these are your different lines. So now what we do is we will just run the analysis for self-weight. Go to self-weight, provide the name of a self-weight and press OK. But we need to import the results from Seepage. So go to results from other cases. Just import your model file. So we have run the analysis in certain folder. We will just import the results from there. So here we have run a seepage analysis. So consider the seepage results. So here you can see this is for steady state and these are for your transient seepage. Just import all the results. Just close them now. So I have imported it twice. So I will just delete the unimported one. Yeah. So this is for results for your steady state, and this is for transient seepage, and for at different times. So let's say we will generate analysis cases now. So modeling is done, just we need to develop the analysis cases, and we need to run the analysis now. So let's say in the very first case, LEM method, use all your layers. So all these layers should be used, and the upstream, so let's say left grid will be used. So we want to run left grid, and we want to run it for only self-weight. And what type of results method, analysis method you want? You want a Bishop method, and your slope is from right to left in the left side. So just press OK and apply. And now let's say right. So to the right grid. So this for the right slope, this is what we have defined, the right grid. So I'm just activating the right grid. And for self-weight, so let's say this is from left to right. So this is from left to right. You need to consider left to right. Just press OK and press apply. So the left SW with respect to self-weight, SW is nothing but self-weight. So only for self-weight how the analysis is running. And now we will apply for the right grid, we will apply steady state seepage. So this is your steady state seepage, and we'll see change the name as steady state and press apply. Similarly, we will change the name to left, and then here change from right to left, and instead of right grid, apply left grid. Press apply. So what you have done is, for steady state results, you need to apply different analysis cases. So basically, in one single model, you can able to run the substability analysis for self-weight as well as your steady state cases. So similarly, you can able to generate for transient seepage. Now I have generated 4 analysis cases. I can run the analysis to find the results. Even the report will be generated. So I have already ran certain analysis for different model. So this is my analysis model, analyzed model. So I will show you the results for different analysis cases. Yeah. So here, yes, it is reading the output file. So once the output file is read, we will show the results, and then I will show you, I will directly jump into the liquefaction analysis in GTSNX. So LEM left. So this is only for self-weight. So for the self-weight, we got a factor of safety of 1.59, and this is a failure surface. It is failing in a leaf and the embankment, and this is how the each and every free body diagram can be. So you can see what is the results coming onto the interslicious forces. You can find the self-weight, and of this particular slice, you can find traction and normal force as well. So all the results can be seen in here. And this is the failure surface on the left side. Now we will see the failure surface to your right. LEM, right? Yeah. So the existing leaf, sorry, this is your existing leaf, and this is your embankment. The embankment is failing on the right side, and the factor of safety is of 2.17. Now what happens is, whenever there is seepage coming from upstream to downstream side, what happens is your embankment will be failing even earlier. That means your factor of safety will be very low. That's what we need to find it. And now we will see the results for different steady state case on the right side now. So the right limit equilibrium method, right side with steady state. Yeah. So here you can see the ferritic line of the steady state, and this is passing through your failure surface of the earlier shown failure surface, and now the factor of safety has been reduced from 2.17 to 1.88. It means the seepage is governing this failure surface, and the results has been reduced from 2.17 as a factor of safety to 1.88. So this is how how much the seepage results can able to have the effect on the slope behavior. And now let's say on the left side we got a factor of safety for self-weight only 1.56, and now since the seepage is going from upstream to downstream, this factor of safety should get increased. Now we will see how it is varying. Yeah, so now the factor of safety has been increased and it is like around 1.95. So the behavior is correct, and we need to see the behavior for transient seepage as well. So let's say on the transient seepage, only on the right side we will see. On the right side transient seepage, this is my phreatic line in the very first state of 68,400 seconds. And you can see the factor of safety is of 2.17 because it is not changing. Only for the self-weight also we got factor of safety of 2.17 even without factor of safety. And now with the seepage result in the very first case, your phreatic line is well below and there is no influence of seepage, so the factor of safety is again 2.16. And now for right side on at 1,29,600 seconds, we got a factor of safety of 2.17. Again, there is no effect of seepage results because it is passing through the riprap and your dam casing is safe. And again, in the very next step, where your seepage is your rapid drawdown is stagnant. Sorry, your transient seepage is same and you're not having any effect of seepage onto your slope. So again, the factor of safety is 2.176, and in the very last step where you got a rapid drawdown, so the water level has been reduced and the factor of safety is remaining the same because the phreatic line is well below and there is no effect of seepage onto your failure slope. So in the transient seepage, you can find that there is no effect on the right side of your embankment, but there can be some effect on the left side. So similarly, you can able to generate different analysis cases onto your left side, onto your right side for steady state as well as transient seepage, and you can able to find the results. That's how simple it is. You just run the seepage analysis in slope module, and you just run the seepage analysis in seepage module. You just carry your module towards the slope module and run the analysis for steady state as well as transient. Even import all your steady state transient results into slope module, and in the slope module run your limit equilibrium method as well as SRM method. In this current model, I'm not showing you SRM, but I'm already having a certain result for finite element cases. I will just show you the results, and then we can directly go into liquefaction analysis. This is your analysis with respect to SRM. So what I have done is I have created a model by directly transferring from seepage module to slope module, and I have run SRM method. Instead of limit equilibrium method, I have chosen finite element method now. So with only finite element method, this is my this is my failure plane. Yeah, you can see this is my failure plane, and the factor of safety is around 3.6. And whenever you go for steady state analysis, steady state flow, yeah, this is how the downstream side is failing. Upstream side is it's not failing, and downstream side is failing. This is how the failure surface is, and this is a phreatic line. And this is with respect to SRM method for a steady state. So we'll see the same results in transient seepage at different times. So transient seepage at 68,400 seconds, we can see the results of maximum stress. So you can see this side is failing because there is certain increase in the water flow, and this is the failure surface, and here you can see the phreatic line. And in order to see the displacement, you can able to see like this. So this side of slope is displacing like about you can see the results by just probing them. Let's say how much amount of displacement this particular slope is being experiencing on either sides. I will just change it into mm. So once the slope is failing, this can able to like go for about 787 mm, and this can able to go for 358 mm. This is what it represents. Once the slope is failing, like it is having the factor of safety of 3.9, but still if the slope is failing, then it can able to go for around 787 mm on this side, that is towards left, and this is towards right. So that's what it represents. And in the next time step, we can see the results of let's say this is my failure surface and this is my ferritic line in the next time step. And in the last time step where you're having a rapid drawdown, we will see the results. Yeah, here during the rapid drawdown, the upstream side is failing. So this is what we can infer it from your strength reduction method. Upstream side is failing because of the rapid drawdown, and the factor of safety is 3.75, and this upstream side is like a failing when compared to your downstream side, because there is a rapid drawdown on the upstream side. And how much the displacement which you can find is, this is what the displacement you can find. You can find around 426 mm because of rapid drawdown. Sorry, it's like 4000 mm. It's mean 4 meters and 3 meters. So because of rapid drawdown, its factor of safety is 3.57. But still, if when it is going to fail, it can able to go like around 4 meters, 3 meters, and in the very bottom, it can able to go for 1.8 meter. So that's what it represents. It means because of the transient seepage, the upstream slope will be failing. Means upstream slope will be vulnerable for the failure, and because of the steady state seepage, the downstream slope will be vulnerable. So that's what we can able to infer from this particular model. And that's it about the coupled analysis in SoilWorks.